So now let's go through the procedure of solving the question. Okay, let's go to the procedure of solving the question. Now, this is what we are looking for. We are saying that the standard procedure currently is that the average recovery number of days is 142. And we are looking for a new procedure in a research that should be less than 142. Okay. So here, we are going to compute the Z values. So here, let's assume that we are testing this at 95% confidence, one tail. Okay. Let's assume that we are testing this at 95% confidence, one tail. Okay. 95% confidence, one tail. Okay. What this simply means is that if I draw my diagram, we are looking for the mean to be greater than or equal to 142. So all this place is our acceptance region, because that's what we are looking for in terms of the null hypothesis. But of course, we allow for a little less. Okay. Reason being that we are sampling and we are not using the entire population. So we allow for a little less, even though we are looking for more, because there can be sampling error. So all this place then becomes our acceptance region. That means that anything that goes below even the allowance we have made here will be the rejection region. All right. Now, if you are testing this hypothesis at 95% confidence, 5% alpha, it means that the Z, and it is one-tailed, it means that the Z value for one-tailed at 95% is 1.645, okay? So it means that on the left-hand side, it will be negative 1.645. There's no right hand. If there was right-hand side like this, that one would be positive 1.645. But it is not, there's nothing like that, okay? It's just one tail. And I showed this in the video before this video, all right? Now, let's assume that we had, let's assume that the procedure we had gave us 140.2 days, right? Let's assume that the procedure we had gave us 140.2 days. Let's assume that the procedure we had, it gave us 140.2 days, okay? Then the standard, the mean, sorry, the sample size is 36, okay? And then the standard deviation is what, 15. So put these figures in your mind, okay? Put these figures in your mind. So the Z value then, remember, the Z value is equal to sample mean minus population mean over standard error. Okay. Now, the number of days we found in our research process was 140.2. So minus the population mean of 142, okay, divided by population standard deviation of 15, square root of sample size of 30. All right, so if you compute this Z value, sorry, the sample size was 36. The sample size was 36. Sample size was 36. So if you compute this Z value, 140.2 minus 142 over 15 root 36, you are going to get negative 0.72. Okay. And if I want to plot this negative 0.72 on this graph here, it will be somewhere here. Because the more we go to the left, the more negative it becomes. Then right is more positive, right? There's like a number line, okay, or a graph. So negative 0.72 will be somewhere here, all right? So it will be in the acceptance region, all right? Negative 0.72 will be in the acceptance region. So it means that we will accept the null hypothesis. We will accept the null hypothesis, all right, because it is in the acceptance region, okay? Now, this simply means that anytime your computed z-value is greater than the critical z-value, we accept the null hypothesis, all right? We accept the null hypothesis, like what we just did, okay? All right. Now, let's do two-tailed. So two-tailed, the same procedure, but now we are going to look at it in terms of the two-tailed, okay? Let's look at this example. A plywood plant makes plywood used in residential and commercial building. One of their products is 3/8-inch plywood, which must have a mean thickness of 0.375. Okay, so here a company produces a plywood, and the standard is that that plywood must have an average of 0.375 inches thickness. So it means that the status quo is 0.375. It must have. So it means that it must have a mean thickness of, it didn't say that it is greater than this or it is less. I said it must have a mean thickness of 0.35. So that's our null hypothesis. That means that the alternative is that the mean is not equal to 0.375. Okay. Remember that in this question, the standard deviation is 0.05. So we are going to compute our z-value. We're going to compute our z-value. But let's first of all draw our curve. Now we are saying that it must have a mean thickness of 0.375. Okay. So because of sampling error, we allow for a little less and we allow for a little more. Because it's of sampling error, because it is equal to, once it's equal to, it means that anything that is not equal to, you reject. But we allow for a little less and we allow for a little more. That is why we have this bounds, okay, as the, so here will be the rejection region, these two places, okay. Now, if we are testing this thing at 95% confidence or 5% alpha, remember that 95% confidence or 5% alpha, and if it is two-tailed, it goes with a z-value of 1.96. Remember that when that thing is two-tailed, it goes with a z-value of 1.96. So here will be 1.96, and here will be negative 1.96. Okay. Now let's compute our z-value. So the mean minus the population mean over standard deviation root n. So in this question, we are testing the population for a mean of 0.378. Standard deviation is 0.05. And then sample size is 100. Okay. Put these figures in your mind. Standard deviation is 0.05. Sample size is 100, and then the sample mean is 0.378. So we're going to have 0.378 minus the population mean of 0.375 all over standard deviation of 0.05 square root of 100. So our computed z-value will be 0.6. Our computed Z value will be 0.6. Our computed Z value will be 0.6. All right. So if I plot the 0.6 on this graph, it will be between 1.96 and negative 1. So 0.6 will be somewhere here. And it is in our acceptance region. Okay, so we accept it. All right, we accept it because it is in our acceptance region. So we accept it. Okay, so we accept it. That is how we use Z value to compute. All right. Now, let's go to the p-value approach, which I believe is also very simple. Let's use the p-value approach. So the probability, assuming the null hypothesis of obtaining a test statistic at least as extreme as the test statistic we calculated for the sample. The p-value is also known as the observed or the calculated significance level. To add a degree of, it adds a degree of significance to the results of the hypothesis test. It is just more than a simple reject and accept. Okay, the farther the p-value from the alpha or the significance level, the stronger the decision. All right. Now let's test this null hypothesis using the p-value approach. So a company packages salted and unsalted peanuts in 16-ounce sacks. The company's filling process strives for an average fill amount equal to 16 ounces. So here, the status quo or the standard is that the average should be equal to 16. All right. Then the alternative will be that the average. So the alternative is that the average will not be equal to 16. All right. The alternative will be that the average is not equal to 16. Okay, so the alternative will be that the average is not equal to 16. Okay, so the alternative will be that the average is not equal to 16. All right, that will be the alternative. Okay. Now, if we are going to use the z-value approach, it will be very simple. If we were to use the z-value approach, we will have just said that the average is equal to 16. So we will allow for a little more and we will allow for a little less. That's if you are using the z-value approach. All right. So if you are testing at 5% level, here will be 1.9, negative 1.96 z-value, and here will be positive 1.96 z-value. Or if you are testing at significant level, all right, the significant level will be 5%. That will mean this place will be 2.5%, and here will be 2.5%. Okay. All right. Now, let's compute the z-value. So if you compute the z-value, all right, if you compute the z-value, and let's say it looks like this question didn't give the standard deviation and all right, it didn't give the sample mean, it didn't give, but I gave the population mean. So it didn't give enough information for you to compute the z value. But assuming that they have computed the z value for you, you had 3.32. 3.32 as your z value. Okay. What it means is that because it is two-tailed, 3.32 will fall here. So 3.32 will be somewhere here. It will be more than 1.96. So the z value of 3.32 is greater than the 1.96 here. So what it means is that we will reject the null hypothesis because it is falling in the rejection range. All right, 3.32 is somewhere here. It is falling here. So that would have been the z-value approach. Let me teach you the p-value approach. So for the p-value approach, we will read 3.32 from the z table. We are going to read 3.32 from the z table, all right? So let's go to our z table. So let's read 3.32. All right, 3.32. So 3.3 here and 0.02, 0.02 here. So 3.32, this is the figure. 3.32, this is the figure. And this curve is actually the shaded region. All right, there are so many z curves, but this z curve is for the shaded region. So it means that this whole shaded region here is 0.9995. And I believe how to read the 3.32, we should know it by now. 3.3 on the vertical, then 0.02 on the horizontal. So we have 3.32 here. And the figure is 0.9995, right? 0.9995. So what it means is that per the curve we read, it means that everything here is 0.9995. Okay, that means that the remainder is 0.0005 because everything here is 0.9995. It means the remainder is 0.0005. And of course, remember that the rejection bounds we have. All right, so let's go over our question again. The question says that here, the question says that the computed z value is 3.32. All right, so from the question, the computed, so we are going over again because of the interruption. So from the question, the computed z value is 3.32, all right? And I just said that, you see, if you draw this, mean is equal to 16. So we allow for a little more, a little less, and a little more, all right? We allow for a little less and a little more. So if we are testing a 5% significance level, okay, we are testing a 5% significance level, it means that here will be 0.025 or 2.5%, and here will be 0.025, that's 2.5%, all right? So this will be the rejection region. This will be the rejection region in terms of probability, but in terms of z values, here will be negative 1.96 like z values, and here will be 1.96 positive, okay? Yeah, so if per the question we have computed our z value and if in the question we have computed our z value, okay, and the question said the z value is 3.32. If we were to use the z value approach, it's very simple. 3.32 will be somewhere here in terms of z value. All right, in terms of z value, 3.32 will be somewhere here. So it is above this, so you reject. But let's use p values. Now, using p values will require that we have to go and read the z value of 3.32 from a table, all right, from a table. So this is our z table. 3.32 means that 3.3 here and 0.02 here. So 3.32 is 0.9995, as I said earlier, all right? And this z table, there are several types. This z table means the shaded region. Okay, so it means that for this z table, it is all this place from the z table, all this place is the 0.9995. So it means that what is left is 0.005. That is here. So technically, what it therefore means is that the z value of 3.32 on the right-hand side, corresponds with a p value of 0.005. So in terms of p, in this diagram, we would have gotten a p of 0.0005, okay? And the maximum allowable error that we allow in terms of p is 0.025, all right? 0.025, and we are still at 0.0005, okay, which is less than the maximum allowable error of 0.025. So it means that we are still lingering in the rejection region. In fact, if your p-value was more than 0.025, you would have moved in here, okay? But it is less than 0.025. So it means that we are still lingering in the rejection region because the maximum for the rejection region is 0.025. And 0.0005 is less than 0.025. So we what? Reject the null hypothesis, all right? So there will be a tutorial video to show more on that. Okay, there will be a tutorial video to show more on that. All right. Of course, because it's two-tailed, one-tailed p-value of 0.05, for the two-tailed together, it would have been a p-value of 0.001 because it's two-tailed, all right? And if you are testing at 5%, the alpha would have been 0.05. And I mean, 0.0010 is less than 0.05. So we will still reject because we are still lingering in the rejection region. Even if you are testing alpha at 10% CRA, you still reject because we are still lingering in the rejection region, okay? 0.0010 is within the rejection region up until 0.1, all right? What I'm saying is that even if we are testing at 10%, what it will mean is that here will be 0.05, here will be 0.05, and here will be 0.9. So a p-value of 0.0005 in terms of one tail, two-tailed, it will be 2 times the 0.0005, which is 0.010, like this. And this one is still less than 0.10 alpha, okay? So all that I'm saying is that the clues you must learn is that when the p-value is less than the alpha, whether your alpha is 0.05, 0.1, or 0.01, depending on which level you are testing. You can test at 5%, 10%, or even 1%. So when our p-value is less than alpha, the clue you must learn is that we reject the null hypothesis. And when the p-value is greater than your alpha, we accept the null hypothesis, Okay, that's for p-value. But when it comes to z-value, when your z-value is less than critical z-value, accept the null hypothesis. And when your z-value is greater than critical z-value, we reject the null hypothesis. So if you do not want to draw curves and those things, this is the simple way you can get your answer without drawing the curve. All right, without drawing your curve, when your computed p-value is less than the alpha, whether you are testing at 5%, 10%, or 1%, reject the null hypothesis. And when it is more than the alpha, accept the null hypothesis. On the other hand, when the z-value is less than the critical z-value, accept the null hypothesis. But when it is greater than the critical z-value, reject the null hypothesis in simple terms, so that you don't draw a lot of curves. Again, we can also test hypotheses when we don't know the population standard deviation. Remember when we were doing confidence interval, when we don't know the population standard deviation, we compute for t instead of z. All right, remember we did that. And then in our t computation, we use the sample standard deviation instead of the population standard deviation. All right, so that's the same thing we are going to do. The same process, the steps are the same. So let's look at this example. A tire company conducted a test on a new tire design to determine whether the company could make the claim that the mean tire mileage will exceed 60,000. So here it is a claim. The word is a claim. All right. So remember, claim, you write a claim in the alternative. So the claim is that the mean exceeds 60,000 or 60. All right. Then the opposite of the claim will be in the null. All right. So the null is that if this was greater than 60,000, the null is less than or equal to 60,000. Okay. Now, we don't know population standard deviation, but we know sample standard deviation to be this. All right, we know sample standard deviation to be this figure, 4.701. The degree of freedom to be 99. Okay, the degree of freedom to be 99. Then the sample size is 100 and the alpha is 5%. Okay, the alpha is 5%. Now, if you are finding t-value of 1 at where alpha is 5% or 95% confidence level, 1 and the t-value for 99 degrees of freedom, you get t to be this. If you have the t table, you can just verify. You get the t to be 1.6604. All right, you can verify from your t table. I've taught that in the confidence interval video. So we are looking for a t-value where we are testing at 95% confidence, 1 Okay, you can just pause the video and check from your t-value, all right? 95%, 1 and the degree of freedom is 99. You get t-value of 1.6604. That is the critical value. Now we are going to compute our t-value. So the formula is, remember the critical value is 1.6604. So the formula for computing t-value is the sample mean minus the population mean over the sample standard deviation, because we don't know the population standard deviation, divided by square root of n. Okay. So when you fix these figures, this is here. The population mean is here. The sample standard deviation is here. Then square root of sample size here. You get a computed t to be 0.3616. All right. Now, remember we are looking for less than or equal to 60. So we are looking for here, but we allow for a little more up to a point. All right, so the t value here, or the critical t value, is the 1.6604. And the computed t value is, the computed t value is 0.3616, right? So 0.3616 will be somewhere here to be less than this. So 0.3616 will be less than this, okay? So once it is less than, it is within the acceptance region. So we accept the null hypothesis, or we do not reject the null hypothesis, all right? We can also check the p-value for the t of. You can check the p-value for the t-value of 0.3616, and it's normally done using Excel. All right, it's normally done using Excel. And if that p-value is more than the alpha of 0.05, we will not reject. So if you use Excel to check, you get a p-value of this 0.3592, which is more than the alpha of 0.05. So we do not reject. Remember the rules I gave you, that when the computed t is more than the critical t, we reject. But when the computed t is less than the critical t, we accept, okay? But for the p, when the computed p is more than the significance level of whatever significance level, we accept. But when the computed p is less than whatever significance level, we reject, all right? Okay, so as I said, the p is found using PA stacks in Excel, okay? All right, so in the next video, I'll be teaching on hypothesis testing for a proportion. So let's meet in the next video. All this series of short videos, we've done hypothesis testing for mean. So we are now going to do hypothesis testing for a proportion.